Welcome to the Cosmic Pie Podcast. So I'm your host, Wayne Barkhouse, and today I'm here with
Robert Moore. Nice to meet everyone.
Hey Robert, this is episode number 9. We are live as opposed to dead, I guess. Cha-ching.
Yeah, you got it right this time.
Here on the campus of the University of North Dakota. So we're sponsored by the Department of Physics and Astrophysics, and it's our pleasure to do this on a weekly basis. Sometimes we're here. Sometimes, like last week, we're not here.
Yeah, well, we were here. We just didn't get on air at the correct time, and I apologize for that. But we're also here in North Dakota, where once again we have snow. We had snow this morning.
Well, it's not summer yet, Robert.
Yeah, I know, but it's the end of March. Come on.
Well, last year at this time, I can't remember. I mean, it's been a while, 12 months. But
12
we've
months.
had a few storms.
Yes,
I remember
we have.
last spring semester.
Yeah.
So that's not really that unusual.
No.
It's a little colder than average and that sort of thing. And people, it came in fairly early. I remember Halloween was beautiful. That was probably our last really warm day.
Right.
And then in early November, I think it turned cold, and then we got some snow in November. And so that seems like a long winter because that snow really didn't have a chance to melt.
And we're finding out that you're being told your sound is really low. So,
Okay, so I crank it up a little bit.
Yeah,
Does that
it's-
sound any better?
I'm not seeing any movement off of your mic. Interesting.
Okay.
It's connected.
Yeah, you have it plugged in.
Yep. Yeah, his mic is on. We're just we're trying to
There's
figure
no
out.
light on the mic, so
Apparently, it's not working. The computer is recognizing that it's there.
oh,
The light came on now, it should be working.
Yep, now it's working.
Okay. I just had to unplug it. When in doubt, reboot.
Always something here on the Cosmic Podcast.
You always got to reboot this stuff, all electronics,
Yeah,
right? And then
yeah.
see what happens. Okay.
Okay. Yeah,
So-
it's showing it's working now.
Okay, good. So that was weird. But hey, the next time we know what to do.
Right.
There you go.
We'll test it next time before we get on there.
Right. So if you do have any questions you'd like us to answer during the podcast, please send your question at the chat. So we have that running now. Now, Robert, before we get into it, just to stress the point that obviously anything we say is between you and I. No one else has to hear, right? Is that how this works? Or?
No, I'm afraid right now it's going out to everybody.
Oh, everybody?
Yeah.
You mean everybody heard everything I said the last few podcasts?
Yeah.
Uh-oh. I got to go back and watch them, see what I actually said. I might be in trouble. No, anything that Robert and I say, obviously, are the direction of Robert and I, and it's no one else telling us to say certain things or not say certain things, but we like to keep things clean. You never know the age of our audience,
Right.
and there's enough other stuff out there that people watch that they're not, things that are
Mm-hmm.
not appropriate, so we want to keep this age appropriate. Now, Robert, on the news when it comes to astronomy, first of all, did you see all that planetary alignment last night? Did you get a
I
chance?
did not go out and look. No offense to anyone, I recommend strongly that you do go take advantage of these events. But Rob's seen Mars and Jupiter and Venus in the sky many, many times. And Uranus, I'm going to sit here and say, if you don't have dark skies and a pair of binoculars, you're not seeing it. So with those factors in effect, I have a little hard time getting hyped up about going outside and looking at
Yeah,
the
I
planets.
I tried looking probably about 25 minutes after sunset last night. And the thing was that both Mercury and Jupiter were extremely low in the west, really low. In fact, it was so low, it was kind of in the muck and kind of around the tree line. We do have some trees in North Dakota.
There are some, yes.
Yeah. And so it wasn't really in a good position to have a good look.
Right.
But certainly Venus is extremely obvious to see to the eye as soon as it starts to get
Yep.
dark. And the moon, and then above that was Mars. So, you can see a lot. And of course, we always see one planet at least, and that's our own Earth.
And that's our own Earth.
Assuming you have, eyesight, of course, right?
Yeah, right.
You have to always got to make that assumption.
Yeah.
But one of the big things that has been on the news lately, and something that's popped up now and again, is this weird object. Oumuamua. So Robert, you want to bring up that first slide?
Certainly.
Now, this is not an image of the object itself. This is just an artist's conception, what we think it looks like. In fact, from observations that were taken several years, well, a couple years ago now it's been, we know that one dimension of this object is many times longer than the other dimension. So whether it's cigar shape or pancake-like in shape, we don't really know exactly, okay?
Right.
The problem was this object was discovered in our solar system, but it was on the way out of our solar system. In fact, it's on what is called a hyperbolic orbit. So a hyperbolic orbit, Robert, do you want to explain what that is, by the way?
All right. Let me switch back screens here because I might gesture and make some. But a hyperbolic orbit means, well, it's one of the conic sections. And so the conic sections are the circle, the ellipse, the parabola, and then the hyperbola. And the hyperbola essentially is what we call an open orbit. The object has a lot of energy. It comes swooping in, picks up speed going around the sun, and then shoots off into oblivion again, into the cosmos. With a parabola, it kind of does the same thing, but it doesn't pick up energy. It doesn't pick up any speed. You're more likely to get an elliptical orbit or a hyperbolic orbit than a parabolic, though.
Right. For the sake of this discussion, then, the important thing is that this object is not bound to the sun.
Okay.
Right?
Yeah, it's an open orbit.
Yeah. In that case, it came in from somewhere, and it's going out in a certain direction. And so it's not part of our solar system. It's a true interstellar object in that sense.
Right.
Now, where did it come from? I mean, people looked at this, and they have some guesses of possible stars that it, but we don't know if it originated there. It could have just passed by that star and then headed in our direction and got here, and then is leaving here, and eventually will go maybe near another star or whatever, depending on where it's actually headed to. The problem or the interesting aspect about this is when people studied this object, it seemed to have bizarre properties. They weren't the same as what we'd expect for an asteroid-like object or even a cometary-like object. In fact, there have been many suggestions by a selected few people, and I would keep it few because that's pretty well, if you think of all the astronomers out there, it's only been a few that have really suggested that this may be a space probe, if you like, something that was built by others, intelligent life somewhere else in our galaxy or beyond, and that this kind of wandering through the galaxy, whether it's making observations or not. I believe it was the Alma array and maybe some other radio telescopes that actually monitored this object to listen for any radio transmissions that it might be sending out. And it didn't detect anything, to the level that it can detect things, the sensitivity that we have with our our Earth-based observations. But there has been a suggestion that maybe this is a space probe of some type. Maybe it's disguised as an asteroid or a comet, right? I mean, if you can build this type of technology, if that's what it is, and you want to hide it, if you wanted to do passive observations, I'm sure you could make it look like it was a natural type of object, at least as best as you could.
Right.
And therefore, it would not gather that much attention.
I was about to say, in fact, I would want it to not gather attention. I might want it to swing around, make observations, and then go on out before it started broadcasting those observations. And, why? Because the aliens that it might find are maybe hostile.
Right. And the thing about this object is that when we track its path, we can understand the type of path that it's on based simply on gravity. So the forces involved on this object are all gravitational forces from the solar system, essentially, mainly the sun, obviously. And if it comes within other planets, and close enough, of course, they will affect its motion as well. But what was discovered in the last several years of observations was that there is some additional force that this object is experiencing other than just simply gravity due to all the bodies in the solar system.
Right.
Now, we see this stuff happening in other cases as well, right? We have comets, for example. We have even asteroids that are affected by how they are warmed up by the sun on certain sides, and as they rotate and so on, that can impart an overall acceleration, as we say.
A thrust.
Yeah, exactly. Almost like little mini rocket jets that are operating.
Right.
Now, this object is the same way, and some astronomers have suggested that what's happening is that there is gas being emitted from its surface. So, like a comet, for example, emits gas and dust particles, that this object is also emitting gas. And anytime you emit something, that's going to create a reactionary force. Just think of Newton's third law, right? For
Right.
every action, there's a equal and opposite reaction. And so it is a rocket-like thing, and when you think of outgassing, and that will change the path ever so slightly, but ever so slightly would be something we could measure, especially after a period of time when it deviates from what we expect,
Right.
right? And we can measure that. And so that's something that has been known of this object lately. And so a recent paper that came out suggests that the altering of its path and what we'd expect is due to outgassing of hydrogen gas.
Mhm.
But others suggest that under the conditions that this object experiences in terms of its energy it receives from the sun, that there would be other signatures of that we would see. And
Right.
it's not consistent with outgassing caused by heating of, let's say, hydrogen molecules, the material on the surface of this object, and some type of outgassing event that's occurring, like comets.
Okay.
Okay.
And Wondergoon has asked a question. Has anyone sent a message at it to see if it responds? He's of the opinion, though, that it is a rock, not a ship or a
Right.
boat.
I'm not sure, to tell you the truth, of anyone that's, there's
not
nothing
heard
that
of
I heard of. I know they've listened.
Right.
And I think to send a message would be, clearly it would intercept our transmissions right here on Earth because they're, multi-directional, right? So they're
Right.
all over, they're broadcasting in all different directions, right? You think of our radar, especially our military radar here on the Earth, that's going all over the place. So if it was a probe, it should, and if it was sensitive enough, of course, it would pick up those transmissions.
Right.
So so we'd be able to see that. But I don't think no one has purposely beamed anything at it, or a high-powered laser or something like that.
Right.
In fact, people have tried to look at, is there a way that we can catch up to the object? It's heading outbound out of our solar system. Is there any way that we can catch up to it in a reasonable period of time, given the technology that we have at our disposal now? The answer is yes.
Oh, it is?
It is yes, but it's something you have to put together immediately and spend a large sum of money, and no one has willing to do that.
Right. Okay.
Right? And that makes sense. You can slap enough solid rocket boosters
True.
to a probe, right, to get it out there as fast as
Right.
possible to the outer solar system, and you'd catch up to it, in a few years or something like that, and then you'd be able to study up close, in situ, as we would say, right?
Right.
But no one, like I said, no one has coughed up the money to do that.
Right. No one
So,
wants to cough up 10 million now.
yeah.
10 million over 10 years. Okay.
Yeah, and
But-
it'd be a lot of money because you got to pay for the rocket launch, right? So you can imagine a launch by the Falcon Heavy or something, right?
Right.
To get your probe up there and then try to catch up to it. And so we can do it theoretically. And I've seen it several papers that people have, published on this, or at least tried
Yeah.
to publish, right? It's preprints. But like I said, it takes money, right? And to be fair, how much money is it going to take? What can you buy? A Falcon Heavy, when they were first tried, it was advertised as $80 million. Now, because it's been very successful, it's been a few flights of the Falcon Heavy, not just Elon Musk's car, right? That's
Right.
gone up. I think the price also went up. I'm not mistaken, but I think he, it's probably 150 million or something now, whatever.
Right.
And there is inflation, obviously, right?
And in addition to the Falcon Heavy, we'd actually probably need to make part of the cargo actually some extra boosters to
Yeah.
really get it
To
out
get it
there and
fast,
going.
and you want to keep the thing with the least amount of mass as possible.
Right.
So you want, the most miniaturized type of electronics and so on. So let's round it off a nice, cool $1 billion. Okay, we're taking donations. So if anyone wants to start sending in money to us, and once we reach that $1 billion, not a million, a billion with a B, then we can design and try to launch such a,
We'll put your name on the gold record we'll put on the side of it.
yeah.
Taking a cue from Voyager.
Don't send the money to me personally because I don't want to pay taxes on that. by the
Right,
way,
right.
But yeah,
Sorry,
you'd have to
folks.
win like the Powerball, right? When it gets over $1 billion.
Right.
Just take the whole winnings and try to, yeah.
Try to get your Oumuamua rocket probe going.
Exactly. Now, and we've had other objects that's been on hyperbolic orbits as well. Do you remember the other one?
I don't remember any off of hand, but I think it was a comet that
Yeah.
was on a hyperbolic.
Borsov,
Okay, that
right?
was
It was
one,
the
right?
name. And there's probably been lots more. Those are just the ones we've actually, seen them and
Right.
plotted their trajectories long enough that we can tell they're on those type of orbits. In fact, in the near future, when the Van Rubin telescope starts operating in Chile, this is roughly an 8-meter sized telescope. It's going to image the southern sky, the complete sky, every 3 nights. And the idea is with such a large field of view and data that we'll have at relatively short period of time, that we'll be able to capture a lot more of these objects.
Okay.
And maybe capture them when they're inbound, and that may give us some time. In fact, it has been proposed, I think the European Space Agency proposed putting up spacecraft in the solar system, in orbit around the sun essentially, that were on
Standby to go intercept.
to go intercept, so you can have like ion propulsion. So ion propulsion is relatively efficient compared to like normal
Yes.
chemical rockets, but you got to have a long lead time for them to
Well,
work.
As it's been described to me, the thrust produced by these ion engines, take a piece of paper and hold it in your hand, and that's the amount of thrust is the push down on your hand. So it takes a very long time for it to get up to speed, but it's very efficient at it.
Yeah, that's right. And we've used that technology for many years now with our own space probes, right? That's nothing unusual.
Right.
And so that could be done. You could have standby spacecraft, and you can have several of them in different orbits, right?
Right.
So if an object's coming in an unusual high inclination to the plane of the solar system, you could have an object that's already at a high inclination orbiting the sun, and it would be in a better position to intercept than it would be if something that was in the plane of the solar system.
Right. It takes a lot of energy to shoot something out of the plane of the solar system, folks.
Yeah, and so that would be one way that you could solve that. Just have these things on standby, ready to go, if you really want to spend the effort and the time and the money to intercept these objects.
Right. Well, I'm just sitting here going, it'd be a good way of actually finally observing things in the Oort cloud. If it's covering that much of the sky that rapidly, even a faint light is going to be seen moving significantly over a significantly long period of time.
That's right. I mean, so the technology, the way it is advancing, it's going to make it much easier to see these objects
Right.
in the future. So we may miss this particular object, but we certainly should get the next ones when they come in, at the right time, sort of thing.
Cool.
So we'll look forward to that. That'll be
Absolutely.
very interesting.
Yeah, all this cool astronomy stuff happening, when I'm getting on up in years, I'm not old yet, but, when we're talking 20, 30 years before these technologies get rolling,
Well,
kind of like, oh man.
Well, speaking about that, one of the sort of significant thing that's going to happen next year in 2024 is the launch of Europa Clipper.
Right.
Now, this is a spacecraft that's going to be making detailed observations of the moon Europa
Around Jupiter.
around Jupiter. And it's going to arrive, I believe it was in April in 2030. So you have to hang on at least till April of 2030 to see this spacecraft make it, right?
Right.
But that's the thing. It always takes a long time for this stuff to happen, and you're like, oh, I wish hopefully I'm still alive by the time that,
Right.
like when New Horizon passed Pluto in 2015, it's like, when that was launched, many years before that, it's like, oh, hopefully I'm still alive by the time 2015 rolls around so I can see what the surface of Pluto looks like.
And then we saw it, and it's like, wow.
Yeah, but it's always another thing, right? And
It's always
another, and
another
another, and another.
And
So
that's science. And
Yeah.
It's the way it should be.
astronomy is neat in that sense because it's always changing. If you're a publisher and you're publishing textbooks on astronomy, you can essentially publish an astronomy book every year.
Right.
Just for the additions, the updated, a variation of it, and the different changes that happen, the new discoveries, and so on. I mean, you can look at the science news that's on the internet, and that's the fastest way we get things now, obviously.
Right.
And almost every day there's something new that pops up, right? With
Right.
the James Webb Space Telescope.
I just wish they wouldn't label it as impossible rings or impossible planet or impossible this.
Well,
It's like, no,
you need people to click on these stories, right?
I know.
Is it
I
any
know.
different than the headlines in major newspapers like the New York Times, 50 years ago?
It's really not.
They sensationalize everything
It's
to
really
death,
not.
right?
Yeah.
And now it's just all on the internet. And you just have, like anything else, you have to watch what you read and try to go to reputable sources, I guess. Right?
Right.
So, Rob, did you want to talking about the James Webb Space Telescope? There's been a recent announcement that just came out a couple days ago that relates observations made with the mid-infrared instrument, I believe it was, on the JWST. Do you want to show that? As the next
Sure.
slide?
Let's click that one on. And so there's the TRAPPIST-1 system.
Do you know something about the TRAPPIST-1 system?
I know a little bit. I happen to know, like this slide is showing, that it was a 7-planet system, which is about the most planets that we found in any one system outside of our own. I knew that it was an M dwarf, and I knew that 3 or 4 of the planets are actually potentially in the quote-unquote habitable zone. So it was a system of particular interest. It's also relatively close at only about, 40 light years, I think?
Yeah, 40 light
Oh,
years.
40 light years.
Yeah.
It's on the slide.
It's on the slide. Now, to be fair, I put the slide together so Robert didn't. So it's not like
Okay.
he's a lapse in memory or something, right? Yeah, so the interesting thing about this system, now, if I remember right, was first detected back in 2016 and from the 2-mass survey, the 2-micron survey. And then Spitzer did some observations of this system. This was an infrared space-based telescope that is no longer functioning. Relatively recently, it's gone quiet because it warmed up essentially.
It warmed
and was
up.
done. And
Yeah.
in some sense, the James Webb is a little bit of a replacement for that telescope. Not quite in full functionality, but a little bit. But when Spitzer observed this system, it detected 3 of those planets, and then it follow-up observations with the Hubble Space Telescope and so on got us to the 7 planets that we know that exist here. So the combination of all the observations that we had at the time. And the interesting thing, if you look on this slide, the top part is an illustration of what we think the system is like. Okay, and this is not exact type of setup that you have here, but
And keep in
it's-
mind that the clouds and everything may or may not be proved to be there, but
But the interesting thing about this system, and this is the comparison, the top slide with the bottom slide, is all of these planets, if they were orbiting our own sun, they would have an orbit that's much closer than even the orbit of Mercury.
right.
So they are all orbiting very close to the host star. Now this host star, as Robert mentioned, is a low mass M-type star. So it's relatively cool surface temperature.
Right.
So to receive enough energy or warmth from that star, then you have to be relatively close to it. At least the warmth and the energy that we need for life forms like us,
Right.
for example. So being in that range where water would exist, both in solid, liquid, and gas form, that's sort of the habitability zone. And so that habitability zone is relatively close to that host star. Okay. So it was one of these systems that, like Robert mentioned, it's relatively close. 40 light years seems like a long distance away, but let's advance our engineering, 500 years from now. We'll probably have space probes that hopefully can do a significant fraction of the speed of light at that time. In 500 years, a lot of engineering can be done.
Right.
And therefore, it might take only 50 years or so to get to this system. Well, that's within the average lifetime of a human being. And hopefully by then, 500 years from now, the average human being will live to be, 100 years old, not 80 or something like it is roughly today.
Right. And even if we don't do those advances, my statement is we've had missions now already where the generation that launched it was not the generation that ended up doing the science with it. So, these types of missions are not out of the question.
Well, let's say 500 years from now, the day that you're born, the mission gets launched, takes 50 years to get there. As soon as it gets there, it will take 40 years for the signal to return. That's 90 years. If you live to be 100, then you'll get the information back in your lifetime.
Yep.
That's kind
You'll
of
get to see it.
Yeah, that's kind of the time scales we're talking about. And of course, the faster we can develop the engineering to maybe get spacecraft that travels even faster, right? Then of course we get there a little sooner. And maybe you're only talking about maybe 41 years for that vehicle to get there, and then 40 years for the signal. So it's still going to take 80 plus years, from the day it gets launched to the day that you receive the signal.
Right.
Because it's not going to travel the speed of light because it would take an infinite amount of energy to do so, and therefore wouldn't be able to happen. But the interesting that observations that happened recently, just a couple days ago then, is the fact that one of the instruments on the James Webb Space Telescope, the MIRA instrument, mid-infrared instrument, looked at the first planet that's closest to this host star, looking for any sign of an atmosphere. In fact, they would measure were able to measure the surface temperature of this planet. And that temperature comes out to be approximately 230 degrees Celsius. Yeah, so let's bring up the next slide. And as a way of comparing that, so you can see there's the planet TRAPPIST-1b is what was measured. And you can tell from this slide that if the planet didn't have an atmosphere, then the temperature that we measured on its surface is the sort of expected temperature that we actually measured from the telescope. So a little over 400 degrees Fahrenheit, if you don't like the Celsius number. Now, if the planet did have an atmosphere, we would expect it to have a cooler surface because it would be able to circulate that heat a lot much more efficiently than it could otherwise, of course, with no atmosphere. And we'd expect a lower surface temperature on the order of somewhere closer to 300 Fahrenheit than what we actually measure. And so therefore, from those type of measurements of what is the surface temperature of this planet, we're able to deduce that it basically has relatively little or no atmosphere.
Right.
Now, what about all the other planets, right? This is TRAPPIST-1b. There's 7 in this system, at least 7 that we know of. Right. So those are ones that need to be measured also. So this is basically continuing work and study that needs to be done to see if any of these planets, is Earth-like in terms of an atmosphere that has one at all, right?
In prepping for this show, I got to admit that I found out that I was under the impression they'd actually done spectroscopic measurements trying to measure the atmosphere and what was in it. I didn't realize they'd gone with a temperature measurement. Yeah,
if you want to go back to the previous slide.
Yep. That one?
No, that one, yeah.
The next one, okay.
Oh, yeah, this one here. You can actually see what they did in terms of their measurements. So on the y-axis on this plot is brightness, okay? And on the bottom is the elapsed time, and the units are hours. Now, what you see is this sort of dip in the middle. So what happens is, as this planet is orbiting the host star, there are times, as viewed from the Earth, or our location, the location of the James Webb is close enough to the Earth, it really matters any difference here.
Doesn't matter, right?
Yeah, there are times when the planet is actually on the other side of the star relative to us. So when you measure the light from the system, then if you just ignore everything else in the system, just think about the one planet and the sun. When that planet is on the back side of that star relative to us, we're just measuring the light coming from the star only.
Right.
Okay. But as soon as the planet moves to either side of the sun, so it moves out from the backside, then we're measuring the combination of both the light coming from the star plus the planet itself.
And let me point out that this does not mean that this planet is emitting in and of itself, but it is reflecting light that would normally have gone out the opposite direction from us. But at the same time, in the infrared zone, it would be a little peak because it has a temperature greater than absolute zero, so it is emitting heat. It is emitting light in the infrared.
Right, that's what I was going to say. So when I say it's emitting light, I don't mean artificial light, number one.
Right.
It's not like there's, a New York City on this planet equivalent, right, and it's emitting light. What we mean is that the surface is being heated up because it's in this radiation bath of the star itself that it's orbiting. And that heated material that makes up the planet is emitting light. That light just is at longer wavelengths in the infrared. In fact, if we could do detailed observations even in the optical, you will see reflected light. So
You
it's
will
not
see
just
the reflected light
right.
there.
It's not just in the infrared, right? In that sense, right? So you have reflected light and actual light that's being emitted because of the material itself has a certain temperature. For technical reasons, we call that thermal radiation in that case.
I mean, I'm going to say a little more on that topic. People don't realize it, but you are glowing. You are emitting radiation, not just reflecting it, but it's in the long microwave wavelengths because you are relatively cool. But as long as something has a temperature greater than absolute zero, it is actually emitting a faint glow of microwave or radio wave or possibly infrared.
Right, so don't do this. This is just a thought experiment. If you ripped off the nearby 7-Eleven in the middle of the night, one way I might be able to follow your motion is to use an infrared camera to track as you run across the roof of the store itself.
Right.
And the reason why, the police departments can do that is because the body itself has a certain internal temperature, as Robert mentioned, and most of our light is coming out in the infrared. So we are a heat source. In fact, the military has that type of instrumentation and look for the signatures, and you can see, infantry walking around on the ground and stuff and see their heat source at night, right, and use them, for targets. But yeah, this can happen, right? The fact that we can detect this infrared light then coming from this planet, and from that infrared combination of brightness from the planet, whose, as you've seen in that slide, it was the day side of the planet that was emitting the light as our view, right? So on either side, we're seeing really the day side of the planet from our point of view when the planet is in this position in their orbits, okay, in its orbit. Then what happens in this case, we see the combination of that infrared light coming from the host star plus the planet itself. And by noting what the star is producing, only by when the planet is behind the star, and then seeing what the combination of the two produce when the planet's on either side of the stars you see in this slide, then we know the contribution of the planet by itself. You just subtract off the star-only contribution.
And from that, a
Yeah.
nice little known, let's see, what would be Wien's law, wouldn't it?
Well, yeah, and the black body.
Stefan Boltzmann.
Yeah, essentially the black body function,
Black body,
right? If you think
right.
of, if you know any physics at all, then it's the black body type of curve you look at. And from that, by fitting a temperature, an intensity or brightness from that, you can fit a temperature, because that's uniquely determined, right? A black body curve. And that allow us to say that, the temperature is so high, as far as we could tell, there probably wouldn't be an atmosphere on this planet. It should regulate the temperature a little better.
Right. I mean, we all are aware, whether we know we're aware of it or not, that atmospheres are pretty good at redistributing heat. Why do we know that? Because there's wind. Okay? And that's all wind is doing, is redistributing heat from one location to another.
What's a good example of a planet that's similar to Earth in terms of its size that does that here in our own solar system?
Venus.
Yeah, Venus. Classic example, right? Completely cloud covered, right? You can't see the surface of Venus in the optical, right? You need to go, use radar and get a radio, right? And microwaves and so on to bounce off the surface.
But you can see the clouds.
Yeah,
You
and
see them zooming around the planet.
Exactly. It has a really high wind on Venus itself, and it's redistributing that tremendous heat, that's from the daytime heating.
Right.
And so the idea is that the surface temperature of Venus would be the same day or night, essentially, because of this equalization that occurs.
Unlike Mercury, for instance, which has no atmosphere, gets incredibly, or the moon even, incredibly hot on the day side, really cold on the night side. Now, keep in mind, as we've mentioned on a previous show, that for we astronomers and physicists, temperature is really just a proxy for us describing how fast the particles are moving. So it's not that you can stick a thermometer out there and get the heat, although sometimes it is. But it's really, even if you have 3 protons in a cubic meter, we can still refer to it as a temperature because of how fast those particles are moving.
Yeah, so one way you could think about it is temperature is a measure of the average motion of things.
Right.
So you'd never want to say the temperature of a single particle. How do you get an average if there's one particle, right?
And you can't.
You can't. So you never speak of temperature that way.
Good point.
Yeah.
But this is why we speak of like the corona of the sun being at 1,000,000 degrees. Well, there's fewer particles in it than the atmosphere of Mars, and the atmosphere of Mars is a better vacuum than the heart of your vacuum cleaner. So, you got to kind of keep these things in perspective is all I'm really trying to hint at, that, you can have a temperature even though there's very few particles there, simply because we're talking about how the average motion of those particles.
Yeah, in other words, as Einstein said, it's all relative.
All relative, yeah.
So, Robert, you had some things you'd like to share with us as well?
Well, I was going to keep the momentum going about these red dwarfs, because another interesting thing has been in the news lately about impossible planets. That is coming about because of papers like this one by Hobson et al. You can see the list of authors on there. And by the way, this paper is open access, so I'm thinking that means that anybody and everybody can go and download and look at this paper. And if you're interested, I highly recommend doing that. But anyway, what this paper was saying is that they found, using transit method and then confirming radio velocity measurements, a Jupiter-sized planet around a red dwarf. Now, the reason that is crazy and impossible is because the amount of material in the disk around a forming star, the protoplanetary disk, scales as the mass of the star. So M dwarfs are around 30% of the mass of the sun. So you would expect then the debris disk around them that's available for forming planets would be appreciably smaller in relation. So these planets are impossible, put that in quotes, simply because there shouldn't be enough material there for them to form, especially not a Jupiter-sized one. And so that's what's going on. And it's not the only paper. There's been, I found 3 or 4, including another one by Canodia et al., where another giant Jovian planet, this one, let me see here, is a little bigger than Jupiter. And again, the M dwarf star it's around is 30% of the mass of the sun. So we're talking a star that, stars pretty much are relatively the same size till you get down to M dwarfs. So this star is only about 4 times the radius of Jupiter. And it's got a planet going around it that's the mass of Jupiter and about a quarter the size of the star, size-wise. So this is pretty exciting news because it starts jumbling up our planet formation models. It starts saying, well, maybe there's more science to be poked at and thought of and worked on our planet formation ideas. So that's always interesting to me anyway.
Well, you can think of what is the most abundant type of star that we find.
And that's why this is also interesting. The most abundant type of star is M dwarf. About 1 out of every 2 stars.
Yeah, so there's way more low mass stars. And by low mass, I mean less than the mass of our own sun.
Right.
That's in our galaxy compared to stars that, even have the mass close to our sun or even more massive than our sun.
Right.
And so when we're thinking about, this leads back to discussion about, life elsewhere, right, in that sense, right? And so you'd wonder, since most of the stars are these low mass stars, is a better chance for life to form on those type of stars than it would be around stars like our own sun? There was a recent study that came out about a week or so ago stating that a lot of these M-type dwarf stars are very active in terms of slow solar flare, stellar flare type of events, right, as they would be for them. And that would be, if that's the case, if a lot of these low mass stars are very active, way more active than our own sun, that may have an effect on the chance of life to survive. And I don't mean bacteria type of life, I mean animals.
Animals, right? Plants, multicellular organisms.
Yeah.
Yes.
That would be a lot harder for them to get a foothold and get going.
Right.
Than it would be, on a planet like we're on around the sun, where clearly it happened. Right?
And Wondergoon has asked the question, can a dwarf star capture a Jovian-sized planet that formed elsewhere, like a rogue planet? The answer is no-ish.
Yeah, it'd be highly unusual.
It would be very unlikely. It would, have to be coming in, its relative velocity would have to be really low compared to with the relation to the star for it to be able to. Plus, it would have to come in at just the right angle. Otherwise, it would actually be a hyperbolic orbit. And it would pick up energy and shoot off.
Yeah, if you discovered one out of a sample of millions and millions, you could almost, maybe that would work statistically. But now with the case where we have several, as you mentioned, papers which show evidence for this.
Yeah.
And I think, as Bill has a question about this, I think that's more in line to what's happening. It would have been a binary star system that formed, right. But of course the one object didn't have enough mass. In order to form a star, you need to have a mass at least 8% of the sun's mass, so you can get the central temperature of the object to 10 million Kelvin to allow sustained nuclear fusion of hydrogen into helium to occur, which we
Right.
call, to be the birth of a star at that point. But if an object doesn't have enough mass, we call those brown dwarfs. So they have less than 8% of the sun's mass. And it's a continuum, right? So as you go down to lower and lower mass, then we just change the terminology. You go from a brown dwarf into a planet. It's a gray area in terms of where that cutoff is.
It is very
It's
gray.
not well defined. And then you can think of going down into planets with smaller and smaller masses, till you're into moon-sized things. Smaller still, you're getting in the asteroids and comets type of realm. Then you're getting in the rocks. Then you're getting into pebbles. Then you're getting into grains of sand, and then finally dust grains that we find in typical interstellar matter.
Right.
So there's a whole continuum of masses.
So in other words, Bill here as Mizuho has hit the nail on the head. We're likely looking at something that tried to form a binary, and just one of them didn't have enough mass and became a planet. But even that kind of gets a little sketchy because, I'll throw out the genes mass.
Well, I mean,
There's a certain mass limit where it has to be larger than that for it to free fall under gravity to collapse. But in this situation, maybe that doesn't apply because it's got the gravity boost from the nearby star, one that did build a star. And it also there's other forces than just gravity at work.
right. So the thing is, you model a pre-solar system nebula after what we know exists. So you model it after the solar system. Then when we start to discover exosolar planets around other stars, you increase your modeling to be more diverse because you have something larger than a sample size of one. Right? Okay. So then at that point, then you can wonder, well, if I have some type of material that ultimately some of it collapses, the central region of this cloud of material or a pancake-like structure material, that would collapse due to gravity, that ultimately forms a low-mass star in the very center, an M-type star then, how much material is left over after the formation of that star? And I think that's where these arguments get into. We don't expect, I guess is what we're saying here, from our very biased view of how solar systems form, because it is very biased, right? That we wouldn't expect Jovian, Jupiter type of systems to form in that type of leftover debris after the star itself had formed.
Right.
Now, in these discoveries that are being made, of course, we're seeing that there are cases where a Jupiter-sized planet can form. But then I would increase that argument and say, okay, what's the chance of 2 Jupiters forming, or 3 Jupiters, or 4 Jupiters?
Right.
One would assume, and I don't know if this is a valid assumption, you know what the word assume means when we make assumptions, right? I'm not going to say it here on the podcast, but you can look it up in Google or something, right?
Right.
One can make an assumption, at least go down this chain of argument, that if the solar system material, right, formed an M-class star, and yet it formed another Jupiter type of planet, that what's to stop it to have even more material in some systems that you form 2 or 3 Jupiters, but wouldn't that increase the mass of the star itself?
Right.
So for very massive pre-solar system nebulas, you'd form a more massive star, and then the leftover debris then could form these type of Jupiters, right?
Right.
Several Jupiters. That's kind of the argument. If you have a small amount of material, you get these low mass stars like an M-class stars, but there's not a lot left over. Okay, you get a Jupiter maybe, but then maybe that's it, or some very low mass stuff that's hanging around that may even be, moon size in that sense, right?
Right.
And if there was a lot more material that could form multiple Jupiters, why didn't it form a higher mass star?
And that's kind of the argument. To put it in perspective, our sun, as massive as Jupiter and Jupiter, much less Jupiter plus Saturn, seems to be, 99% of the mass of our solar system is still the sun.
Yeah.
So how did this little M dwarf that's only 30% of the size of the sun mass-wise form this massive planet that is now a significant portion of its own mass? And that's the question. And
Now, this star is not in a bizarre environment. Bizarre, I mean, unique and not unique, but in a really highly unusual environment, like in the center of a globular star cluster.
right,
Because their capturing can occur a lot because of the high density of stars,
right.
right?
The high density of stars means there's a lot of gravitational interactions, and that slow relative speed that I was talking about when the Wonder Goon asked the question, can happen a lot more readily, a lot more easily, and so the Jupiter's object falls into an orbit around the star.
Yeah, and so in that type of environment, you would expect more of this type of body capturing and escaping, from various systems to occur all the time. In fact, we know globular clusters, which are just a high, dense, packed region of stars. There's almost 200 of them that are in orbit around the center of our galaxy. They contain upwards to hundreds of thousands, even a million stars.
And they kick out stars all the
In
time.
fact, I like to say there are and inside these globular clusters, the density of stars is so high, and they're relatively nearby, that there's no nighttime if you were on a planet orbiting one of these stars.
Yes.
Because in the so-called night, there'd be so many stars that are relatively close by, it would light up the surface of the planet like it was almost daytime.
Yep.
So it'd be highly unusual. In that type of environment, you'd have a lot more of these, two-body interactions that's occurring.
I never thought about it. It might actually start resembling the outer electrons in the case of a metal, where they just
migrate around.
migrate around a little.
So we have the conduction of stars.
Conduction
Is that
of
what you're
planets.
thinking of?
Probably not, but
But it's interesting. I mean, they evaporate, right? And what happens is the higher mass stars sink to the middle,
and the lower
mass
get kicked
segregation,
out.
and lowest gains escape velocity and get kicked out of the system. So over time, they evaporate just as they're through
Yeah.
normal,
It's-
dynamical interaction with gravity.
It's like our own Earth is bleeding hydrogen,
Right.
Because the hydrogen is light enough that it actually, and the Earth's gravity isn't strong enough to hold on to it. So the hydrogen escapes out to the top, picks up a little more energy from now the ultraviolet photons coming from the sun, and off it goes.
Yeah, in fact, you can use that argument that Mercury may have an atmosphere a lot earlier on in its history, and that all evaporated off being so close to the sun and received that energy that essentially, lost its atmosphere.
Right.
Right. In fact, we know something happened to Mars
We know something's happened to Mars.
because there's evidence of dried up riverbeds, as far as we can tell, on the surface of Mars. People tried to get around that by saying it's the movement of frozen carbon dioxide, that slowly moves on the surface that would grind out these things that would look like dried up riverbeds and stuff. I think that theory has pretty well been put to
pretty
rest.
well been put to rest with the finding of minerals like hematite and a few others that are definitely hydrous minerals.
Yeah, so we know atmospheres of planets do change radically,
Right.
and I'm not talking about human intervention here, of course.
Right.
So we're talking like planets like Venus, for example, and even planets like Mars would have had their atmospheres altered dramatically since the early years of the formation of our solar system 4.5 billion years ago. So so the finding of these type of planets then is extremely interesting, and certainly for the search for extraterrestrial intelligence, the SETI searches, for example. You have finite resources. Are you going to target them at M-class stars where they're so numerous, so there's lots of targets?
Mm-hmm.
Or do you believe that the conditions are such in those type of systems that they wouldn't support intelligent life on any
Right.
planet? It's just too harsh.
Well, I mean, how active are M dwarfs? And the answer to that is that they've found M dwarfs where they've detected sunspots on them due to the dimming of the star in visible wavelengths, while X-rays it's hotter. They have found sunspots on these M dwarfs that are 1/3 the size of the star. And sunspots are where you get your flares. Sunspots are where you get your large prominences. So it's estimated that the prominence from such a sunspot would probably be bathing anything within about the distance of Mercury's orbit around the sun. So there's a lot of reasons to look at M dwarfs, but there's a lot of reasons to say, yeah, you're not going to get much going on around.
Well, it's unfortunate too, but because M-class stars are so abundant, statistically, the chances are that the nearest star to our sun is probably going to be an M-type
dwarf.
star, and it is Proxima Centauri.
Yep.
That's the one that's just over 4.2 light years away. And we know because we study, where it's relatively close, a lot of people have interest in that type of star, and there's evidence for planets around that star, that in that case, because of our detailed observations of those stars, we know that Proxima Centauri has gone through outbursts in the past.
Yes.
And we know that it can be extremely active.
Right.
In fact, it could be harmful to life, But of course, you'd have good aurora displays, as Vincent
As
pointed
Vincent
out,
points
right?
out. You'd
But
have
if there's no
wonderful
life to
aurora.
appreciate it,
Right.
it's like if a tree falls in the forest and nobody's around to hear it.
Did it really fall?
Of course, it fell. Well, we don't need life to be able
But
to.
did it?
If there's no life in the universe, did the universe really exist?
Right.
I'm talking about other universes, not
Right.
our universe. Clearly,
But,
we're here, so there's life in this one.
But this is why I'm one of those that I'm a proponent. I think life will be found to exist around M dwarfs. I mean, we've got life that forms. We've got bacteria that forms inside nuclear reactors.
Yeah, extremophiles.
Okay? Extremophiles. So I think we will find M dwarfs with planets with life around them. Do I think it will be complex life? Probably not. It's just not a pleasant environment for complex life. I'm just spitballing here, but I would say biologists might be able to check me on this. But siphonophores, essentially colonial single-celled organisms that can form a colony and semi-specialize between them, might be able to form. But anything more complicated than that would probably be just blasted by X-rays and ultraviolet radiation and charged particles at high energies. And
Well, the SETI people will be disappointed because they're looking for life forms that have built transmitters
right,
and that would send out signals.
and that's I would be surprised. I would be amazed, honestly, if there was that level of complex life found on a red dwarf.
Now, to be fair, we always have our biases.
Absolutely, we've got a sample size of one.
Yeah, that we know life exists in the universe. It's only here. And so we don't know of all the different conditions that life can arise in that are different from what we did here on Earth.
Right,
So we always got to be careful of that statement.
and yeah, that's what I'm saying. My opinion.
Right. So I would never, given limited resources, I would never rule out checking those type of stars as
heck no.
targets.
Oh no.
But
Yeah.
but I'd be looking for a G2 type of stars first.
Right.
Stars that are just like our sun.
Or maybe K.
Yeah. But that
I look around some
the first
Ks.
targets would be like our sun.
Absolutely.
You just go and then you broaden out, right?
Right.
And look at other things that are similar to our sun but not the same, and then keep going outwards in diversity type of thing, right?
Right.
Increasing your target size if you don't find anything.
Mm-hmm. I agree.
I mean, people have, suggested that for all of the conditions to be conducive to form life as we know it, as it is here on the Earth, that if you add up from a statistical point of view what you need to be on a planet that's at the right distance from the host star. The host star needs to be the right type of star, right? That you need to have, other planets in that planetary system that will clear out any chance of being constantly bombarded by asteroids. So life starts getting a foothold, and a large asteroid hits the planet, wipes out all that life. And you wait hundreds of millions of years for life to get going again, or whatever long it takes, and then it gets wiped out again. And so you need a large body that kind of can gravitationally perturb those type of objects from not constantly raining down on the Earth. You need stability in terms of a rotation axis, which is actually provided by the moon, for example. All of these conditions need to happen, and that the chance of life arising on other planets is extremely rare.
Right.
Right? That's the one,
Yeah.
the pessimistic view if you're looking at life being abundant in the universe.
And I'm a little more optimistic about life than that.
Yeah, and what I mean by life is not bacteria. So
Okay.
I mean advanced animals.
Advanced life,
We're talking
yeah.
about animals, right? Things that will build, spaceships to travel the stars and so on eventually, or try to, right? That kind of life form. That it's extremely rare. In fact, maybe it's only one in every galaxy.
Right.
Or if you're more optimistic, maybe it's a few, but then the average distance between us and them is so far
It's prohibitive.
that we haven't done anything yet that would allow us to have a good chance of detecting any type of signal that may come from them or whatever. And so that's the thing you have to kind of think about. So we just don't know.
We don't know.
That's the conclusion.
In the end, we don't know. We're making guesses. There may be educated guesses, but they're still guesses.
And that's just the argument for why you should observe,
Right.
because we could be completely wrong.
Absolutely.
Right? I mean, there could be life within 100 light years that know we even exist and have decided to be quiet and not let themselves known.
Right.
And that's the argument that a lot of people have suggested in the past, and I think we also mentioned this in previous podcasts, like Stephen Hawking, when he was alive, said you don't go into a jungle and start hollering and let the animals know that you're around. Maybe you want to keep quiet because you're not sure of the danger that's out there.
Right.
And so,
I mean, that could be an interesting scenario. Maybe I ought to put that in a story.
yeah, you could
Where
call it
a nearby civilization actually is going shh and lobs a few nukes at us. You're too loud. You're going to bring it here, and we're next door. Stop it.
I mean, that's countless sci-fi stories. You think of the Borg on Star Trek, for example, and so on.
Well, that's what I'm saying. These aliens aren't really even aggressive. They're just, you're a neighbor. You're the next tree over, and you're screaming. You know.
And you know that the odds are that some life form that if they actually travel or traverse interstellar distances and get here, for example, they're going to have advanced technology. So any type of military that you may have is going to look extremely primitive probably to them.
Right.
So there's not a lot we're going to be able to do probably to defend ourselves.
I've often laughed and joked about people, and I'm kidding, but you know, if the aliens did show up, you know, yeah, my attitude is I hope they think I'm a neat pet because I know who I'm betting on.
Well, remember War of the Worlds, right?
Right.
That was advanced, right? And there was the microbes, the bacteria, the earth diseases and stuff that wiped them out.
Wipe them out.
So it's just something you never even think about, right? But then again, in a real situation like that, I mean, advanced technology, advanced life would know not to come to the Earth's environment without protection.
Without protection.
Right? Because, you know, they don't know how susceptible they would be to the, type of...
To the microbe.
Yeah.
It'd be like we would do if we found a planet with life. We'd take all kinds of precautions against the microbes there.
And actually, we're doing that now, right? Because one of the short-term goals that we have is the fact that we're going to ultimately bring back rock samples from Mars. In fact, we're now making caches on the surface of Mars of rocks, of samples that we're going to pick up. And I know in the recent NASA budget that came out relatively recently, the other week, there was money in place to build that spacecraft that will go to Mars, pick up some of these samples and return them to Earth. Now, people have argued, if we return them to Earth, do we really return them to Earth? I mean, to the actual surface of the Earth. What happens if there's something on those rocks that's extremely harmful to Earth, to biological systems? Shouldn't we return them to maybe a space station or some orbiting vehicle where we can examine them in detail to make sure they're safe enough?
Right.
So that's a real issue, the contamination effect. You see, in fact, during the Apollo program, both Apollo 11 and 12, I mean, the astronauts had to be quarantined for a period of several weeks, right, after they returned from their mission. And same as all of the equipment that was there and the rock samples and so on. Now, I've read some stuff about the Apollo mission that said essentially that the type of contamination actions that they took were so rudimentary and crude that anything really couldn't escape. It was not like you're on a level 5 containment, building or something, right? That if there really was germs or other things that would have came from some of the material, that would have got out anyways into the Earth's environment, right? But I think the scientists who were, if you talk to them, they would have said, it's a near vacuum of space on the surface of the moon, essentially, that the probability of something surviving is pretty low. But again, we're biased in all this, so we have to be very careful what we say.
Right.
But there is going to be a lot of talk, whether it's safe to bring back, material and soil from other planets in the relatively near future, in just a few years from now, right? We're going to spend money on, building areas where we can contain this material before we have a chance to examine it in detail to make sure it is safe in our environment. So that is stuff that we're talking about now.
Excellent.
Yeah.
I'm glad they're talking about it now instead of waiting till,
waiting.
Hey, it's in orbit around Earth. What do we do with it?
That's right. Well, if you want to talk more or learn more about physics, astrophysics, astronomy, all the neat type of science that we do here at UND, please, if you're at that level, maybe you're in high school and you're thinking about wanting to get into a program and your undergraduate sort of degree, then please consider coming here to the University of North Dakota, and in particular to the College of Arts and Sciences, and if you like, the Department of Physics and Astrophysics. We welcome you with open arms, and there's a lot of interesting things that are happening now and will continue to happen in the near future. And so our next podcast will be next Tuesday, April the 4th. Unfortunately, I will not be here, but I understand D. Smith will be filling in for me. Yep. So those who would like to have him on the podcast, he will be returning. So that's at 3 p.m. Central Daylight Time, since we're now in the daylight time. And as always, we always leave you with a quote. So today's quote is actually from, and it's fitting, Carl Sagan.
Carl Sagan.
And his most famous quote would be, "The cosmos is all that is, or ever was, or ever will be." Thank you for listening.
Thank you for joining us. Y'all have a great day.